Hi all. I thought we might need a few more examples of integration by parts, and in particular, I wanted to show another method that you can use for particular integration by parts problems, particularly ones where it's a problem like the example that we have listed here, x squared or x cubed times sine of 2x. This method works particularly well if you've got x to a power and e to the x, or if this is sine of x or cosine of x, particularly any sort of variation of that, but it works very well if we've got this x to a power of some sort. And so this is called the tabular method. And so what we're going to do is make a table. And in the first column, we're going to list the terms. And this is just going to be like first term, second term, and these are the terms of our integral. Fourth term, fifth term, sixth term. We'll write several here. We don't know exactly how many we're going to need. And then in the second column, we're going to list the signs of each of those terms. And where the signs come from is from our integration by parts. The first term from integration by parts, we get a positive value, so that's going to be positive. And then the second term, we get a negative. If we continue on and have to do integration by parts several times, the third term will be positive, the second term will be, or the fourth term will be negative, and the terms will sort of bounce back and forth between being positive and negative. So these are more just a reminder of what those signs are going to be. And then our fourth column here, this is going to be our u, which is going to be our derivative column. So we take the derivative of u. And then our third column is going to be our dv column. And this column we are going to be taking integrals. So we're still going to pick our u and our dv like we normally would. And we are going to use that same, technique and idea of that what we're hoping for with u is that each time we take its derivative, that we get a simpler function. So we're going to pick x to the third, and then we're going to differentiate it, and we're going to go until we get 0. And this really is the hope, that we eventually get to a column where we are a row here where our derivative is 0. That's really what we want. And that's why this method is really good when we have access to powers, because we can make that our u. And eventually, it takes a little time, but eventually we get down to that derivative being 0. And then our dv is still going to be what's left in our integral. So it's going to be that sine of 2x dx. And then when we take the integral here, we are going to get, I want to state that, we're going to get negative cosine of 2x, but we're also going to get times a 1/2, because we have to do substitution to take that integral. We saw this several times in class with our e to the 4x and e to the 2 theta. So just a reminder that we have to use a u sub here to be able to get that integral. And each time we take this integral, we're going to continue to get a 1/2 in there. And you can also put that 1/2 out in front. So now when we take the integral again, we're going to do the integral of this negative cosine of 2x times 1/2. So we can put that 1/2 out in front. We're going to get another 1/2, and we're going to get sine of 2x. Now we're going to take the integral of this guy, and we're going to get positive 1/4 times 1/2 cosine of 2x. And we could keep going with this. Now we're going to take the integral of this. So we're going to get 1/8. Again, that's just from multiplying our two coefficients we already had. And we get another 1/2, and we're going to get sine of 2x. And we can keep going, but we actually can stop at the same spot where we got our 0. We'll see why here in a second. So this is our stopping point. So now our integral is going to be, so the integral of x cubed sine of 2x dx. So kind of basically what we did here is we did that process of integration by parts several times, kind of in advance. And then, so remember, we want to do u times v in our integration by parts. Well, that is our x to the third times our negative 1/2 cosine of 2x. So we get x cubed plus negative 1/2 cosine of 2x, and its sign is positive because we went with that first row, but down with that multiplied by that second row. Then our next term is going to be negative, and it's going to be, again, that 3x squared multiplied by the term down in the second column there, or the second row, or the row right below it. Okay, so we're going to get minus 3x squared times negative 1/4 sine of 2x. Then the next term is going to be positive, and it's going to be 6x times our 1/8 cosine of 2x. Then the next term, let's see, we're going to run out of colors. Nope, we're good. It's going to be negative, and it's going to be 6 times, then again, that 1/8 times 1/2. So we are going to get minus 6 times 1/16 sine of 2x. Oh boy. And then we stop at 0 because it would be positive term, but we would get 0 times, it doesn't matter what's sitting here because we would get 0, and that's the end of our integral. So this is one where we would have to use integration by parts 3 times, but the table helps us set this up so we can kind of do it all at once, take our integrals, take all our derivatives, and remember what signs we should get so that we can just write out that we get, okay, negative 1/2 x cubed cosine of 2x plus 3/4 x squared sine of 2x plus 3, that's also going to be 3/4 x cosine of 2x minus, that's going to give us 3/8 sine of 2x plus c. And so we can double check this, make sure that it's right. We could check it in Wolfram Alpha. We could check it with using integration by parts sort of our normal way, but we, like I said, we would have to do it 3 times. So this does work really nice when we've got, like we said, integrals that, look like this, where it's that x to a power and an e to the x, cosine of x, dx, any of these ones, it works really well. It doesn't work all the time because the whole sort of point of this method is that we eventually get 0 in one of these columns. And that's not always going to happen with integration by parts. So let's take a look at another example here. If we've got, say, the integral of e to the x cosine of x dx, and we go ahead and try to make our table, and I'm not going to do the terms column anymore. You can still do that, but I'll do the signs. And it's kind of nice to do positive, negative, positive, negative, and change the signs just so that we're really paying attention to what we're doing there. And then we're still going to pick our u and our dv like we did before. So we'll pick our u, we'll pick our dv, and we're going to differentiate this first column, and we're going to integrate this second column. And we talked about this in class, that it really doesn't matter in this case which one you pick for u and which one you pick for dv. That really is up to you. It's nice to pick e to the x, particularly for its integral, because it's super easy to take. Its integral is e to the x forever and ever and ever and ever. And remember, if we had a coefficient on that x, we'd just be getting, that reciprocal of that coefficient times our e to the x, or e to the, coefficient x over and over again. And taking the derivative of cosine, we get negative sine. Taking the derivative of negative sine, we get negative cosine. Then we get back to sine. And, this is something we've seen before, that it, cycles through. But what happens is that neither column ends up giving us 0, so we have no place to stop. We would just keep going with this forever and ever. So this is where we're stuck back at going, okay, we've got to use our integration by parts. And this is also one that ends up giving us that sort of recursive definition. Sorry, trying to write and talk are not always the good action here. So here, our u is still going to be cosine of x, so our du is negative sine of x dx. So, that's just the work that we were doing here in the first two parts of the columns. And the dv dx is going to be e to the x, or the dv is going to be e to the x dx, and so v is e to the x. So we're going to get the integral of e to the x cosine of x dx is e to the x cosine of x. Again, that's our u times our v, so our u times our v, and then minus the integral of v times du. So v times du, that's what we get here. So we have e to the x times negative sine of x dx. So cleaning this up, we get e to the x cosine of x dx is e to the x cosine of x plus, oh, we end up with plus, that's always nice, e to the x sine of x dx. So we kind of end up basically where we were before, but that's where we say, all right, let's still pick u to be that sine of x and dv to be e to the x dx. And then we are going to have that du is cosine of x dx, and v is e to the x. Now, if we were, well, let's continue on here before we get to that. So our integral now is e to the x cosine of x dx. We have our part that's already done, our e to the x cosine of x. And then we have plus, again, our u times our v. So we will get e to the x sine of x, and then minus our v times our du. So we'll get the integral of e to the x cosine of x dx. And this is the one where we've ended up kind of right back where we started. We've got that same integral on both sides. And in terms of the table, we could actually kind of use it to help us a little bit, but we could also kind of see how it works here in terms of the signs. So notice, our first one here, e to the x cosine of x is positive, so positive, and then it's cosine of x times e to the x. Our second term here is e to the x sine of x, so we would have started out with negative, multiplied by a negative sine of x, and then times e to the x, so that's how that becomes positive. And then in our next term, we've got positive negative cosine of x e to the x. Notice that's kind of what we got right here. So that's all right, but here's where we're kind of sitting, and we've got those two integrals on both sides of our equation that are equal. So this is where we can add that to both sides. So e to the x cosine of x dx plus e to the x cosine of x dx. These both have a coefficient of 1 on them. So we end up with 2 times the integral of e to the x cosine of x dx is equal to e to the x cosine of x plus e to the x sine of x. And so just a couple other things. We don't want 2 times our integral. We just want our integral. So we need to multiply both sides by 1/2 so that we get the integral of e to the x cosine of x is equal to 1/2 e to the x cosine of x plus 1/2 e to the x sine of x, and then plus our constant c. So the tabular method, like I said, it works really nice for certain problems. These ones, in particular. Sometimes we still just have to use regular old integration by parts to get what we need, particularly on these ones where we kind of get into a circle. We for sure have to use our regular integration by parts there.